Hello students, let us start with our next unit, input output organization. Before getting into input and output organization, let us see that what you mean by peripheral device. In this peripheral device, we will be coming across this term called IO subsystem. It provides an efficient mode of communication between the central system and the outside environment. So we are going to have a particular subsystem which is known as an input output subsystem. This subsystem is used to provide a mode of communication. It will be used for providing the communication between the central system, that is nothing but your CPU's the processor system, with the external world, that is nothing but your external devices which are connected to your CPU. So this is that is IO subsystem. Next, what actually you mean by peripherals? Peripherals is also known as an IO device, input output device. So you people have already came across what do you mean by input and output device in your previous classes. So the input and output devices are nothing but input and output devices are nothing but the device which gives the input information, that is nothing but it gives the information to the processor. So the device which is used only to give the data to the processor, then that is known as an input device, and the processor gives the info return back the information to the device. So the device always takes the data from the processor, then that particular device is known as an output device. So there are many input and output devices which are connected to your CPU. So like for example, you are going to have a monitor. Monitor, you know that monitor is nothing but it is a general LCD screen. Okay, or you are going to have previous days CRT. So you are going to connect, which is acting as my output device. Okay, always processor gives the data to the monitor. Next is keyboard. Keyboard will be acting as an input device. Okay, when I talk about my keyboard input device, I do have light pen, mouse, touch screen, joystick, digitizers. So these are acting as an input keyboard. Next, we are going to have a printer. A printer is nothing but your hard copy device, which is used to print the in whatever the processor gives the data. That data will be printed as an on a hard copy on a paper sheet. When I go with the printer, I do have dot matrix, thermal inkjet, laser. Later on, we are going to have the storage devices also. Storage devices are like magnetic tape, magnetic disk, optical disk. So those are nothing but a storage device which is used to store the data. So these are the few input and output devices which are attached to the computer. Now whenever these devices are there, we have used a term called IO subsystem, which is used for the communication between these IO devices and to the processor. So to interface this particular input and output device, we use an IO interface. Interface is nothing but a conversion of a signal from a may be required. Why? Because the way of communicating of your input and output, input and output language, device language and the processor language may be differ. Okay, the speed of operation may be differ, the way of representing your data will be differ. So to make it common, to make a to make to communicate, we need to communicate between this input and output device to the processor. We require an interface which translates the input output device language into the processor language, processor to the input output device language. So that means that a synchronization mechanism may be needed. Why? Because your input and output devices might be slower than your processor. So at that time we need to synchronize. At that time we require to synchronize your input and output devices. So we require an synchronization. So synchronization it will be done by using a data transfer rate of the peripherals is usually slower than the transfer rate of the processor. Just now I have told you your input and output devices, your data transfer rate, that is something, but your speed of operation is slower than the processor speed of operation. Okay, then the data codes and the formats in peripheral differs from the word format in the CPU and memory. Okay, so and the formats which you are going to use in the peripheral, the way of language or the way of representing your data in your peripherals input and output device may be differ from the CPU or the memory. Okay, so for that one also we need to come across with the data codes and frames. So we will be using a common format, and we are going to use that particular format for the transferring of the data from the IO device to the CPU and the memory. Next one is something which is the operating modes of peripherals are different from each other. Each peripheral must be controlled so as not to disturb the operation of other peripherals connected to the CPU. So and as there are many input and output devices connected to the processor, only when a processor wants to send the data to the monitor only, then the monitor device should be in under picture, whereas the rest of the input and output devices should not be getting disturbed. They should work in a normal mode of operation. So that particular operating mode we need to keep it in practice. So doing this all this operation we will be going with an IO input and output input and output interface. So each peripheral must be controlled as so not to disturb the operation of other peripherals connected to the CPU. Okay, next one is what interface. A special hardware components between the CPU and the peripheral supervises and synchronizes all inputs and output transfers. So we will be using a particular special hardware unit which is acting as an interface between your input and output devices and the CPU. So that means that it will be acting as an interface between the CPU and the peripherals. So now what is IO bus and interface module? Let us get into the IO bus and interface model. How this IO bus and interface model will be going to have and how they will be going to communicate with each other. Now when we talk about IO buses, we do have three buses are there. One is nothing but your data bus, second is nothing but your address bus, and the third one is nothing but your control bus. A data bus is used to carry the data, address bus is used to carry the address, control bus is used to carry the control information from the processor to the CPU. Next, when we talk about my interface model, so this interface model is nothing but you are going to have a small VLSI chip. So using this VLSI chip, we are going to have a interface module. In this interface model, we'll be going to have SCSI, that is nothing but a common small computer system interface. You are going to have IDE, integrated device electronics. You are going to have Centronics. You are going to have RS-232 cable, or you are going to use an IEEE 488 GBIB. So these are nothing but a different interface modules. You are going to use it to communicate between the CPU and the peripherals. Now if you see here, this is the block diagram of this particular IO bus and interface model. So you are going to have a processor, IO buses. Okay, you are going to have the interface modules. Then for this interface module, you are going to connect your input and output devices like keyboard, monitor, printer, magnetic disk, magnetic tape, so on. You are going to connect it to the bus. The same block diagram represented over here. Okay, the keyboard gives the information. This keyboard information will be converted into processor language, and it is placed on the bus, and the processor reads the data. Otherwise, you will be using a memory unit. From memory unit to the IO devices also, if we want, we can communicate it. Next one, now we go with an IO device or IO communication. We will be using an input and output commands. So this input and output commands are four types. One are nothing but your control command. Second is nothing but your status command. And third is nothing but your input command. And fourth is nothing but your output command. So this input output buses versus memory bus. Before getting in IO device, IO bus versus memory bus, let us see that what actually you mean by commands. These commands are nothing but a control. It will use to control the operation. It is need to give the command to the input and output device. So there are different commands. That is nothing but your input command. That means that input command is nothing but your it informs us that there is an input data is available. Output command is nothing but your there is an output data, that is nothing but your you are going to read the data, so that data is available. That is nothing but your output command. Next is nothing but your status command. Status command is nothing but it gives you the information that as of now what is the status of your IO device. Okay, whether it is under ready state or it is under a halt state, that is nothing but wait stop state, or it is performing some other task. So now it cannot read the data or write the data. Okay, so that status of that particular IO device will be given by using the status command. Next one is nothing but your control command. So control command is nothing but how you are going to control the information. How you are going to control the communication. So what are the control signals? Now you will be saying that yes, now start reading the data. Okay, now stop reading the data. Okay, I am only sending 8 bits of data. So those are nothing but your control commands which you are going to give it to the IO devices. Okay, now let us come with your there are two types of basic buses. As we have seen that there are three buses are there: data bus, address bus, and control bus. So that is common, but apart from this one, we again classify the buses into terms of two types. One is nothing but your input output bus, and the second one is nothing but your memory bus. Same, those three buses will be coming into the picture. Just when we communicate with IO devices, we say that buses as IO buses. When we communicate with the memory, then we say that buses, same buses as a memory bus. Okay, why we are differentiating and why we are using? Let us see that in the coming slides. Computer buses can be used to communicate with memory and IO devices. So your computer bus, that is those data bus, address bus, and control bus is used to communicate between the memory as well as IO devices. So use of two separate buses, one for memory and other for IO processor. Okay, use one common bus for both memory and IO device, but have separate control lines for each. Okay, so that is known as an isolated IO or IO mapped IO. So when we talk about this IO bus and memory bus, I can use separate two buses. One for memory data translation. I will be using this one bus. Another bus for IO process. Another bus for your IO processor. Okay. If not, that is not the case, then we will be using a common bus. Whatever the bus is there in the processor, the same bus will be using for memory and IO devices to translate the data, transfer the data to and fro. But we will be using a separate control lines for each. So that type of bus architecture is known as an isolated IO or IO mapped IO. Examples of IO interface are nothing but your four. You'll be going to have one of the main important IC known as an 8255, which is nothing but your programmable input and output device controller. This in depth of architecture you will be studying in your next semester in MP microprocessor microcontroller subject. So you don't require in depth of getting into this one. Next, when you go with the data transfer modes, we are going to have two data transfer modes. One is known as a synchronous data transfer mode, and the second is known as an asynchronous data transfer mode. So your data transfer modes are of two types. One is synchronous data transfer mode, and the next one is asynchronous data transfer mode. In the synchronous data transfer mode, all the data transfers occurs simultaneously during the occurrence of a clock pulse. So, as soon as you give the clock pulse, the complete data will be transferred. Transfer of data will be going to occur simultaneously. Registers in the interface share a common clock with a CPU register. So, whatever the registers are there in the interface block, that interface block will share the same clock with the CPU registers. Okay, so once we give a clock pulse, based upon the clock pulse, your data transfer will be going to occur. That is known as a synchronous data transfer. Asynchronous data transfer is nothing but internal timings in each unit is independent. That means that your process CPU and the interface in each of this unit you are going to have internal timings as independent. Each unit uses its own private clock for internal register. So each of this unit will use its own private clock. It will be going to use its own private clock for internal register. You will not be going to have a common clock pulse in the as you are there in the synchronous data transfer. This is nothing but your 8255 block diagram, which we don't require it. Let us comes with your modes of transfer. The data transfer to and from the peripherals. Your data you are going to transfer it from to and from the peripherals. Based on that transfer modes, we are going to have four different data transfer modes. One is nothing but your programmed IO, interrupt initiated IO, direct memory access, CIO processor. Okay. So data transfer modes are of four types. One is nothing but a programmed IO, interrupt initiated IO, direct memory access, or you're going to have the IO processor. Now let us see one by one. Okay, let us start with an interrupt initiated IO. When I go with an interrupt initiated IO is nothing but you are going to initiate an interrupt signal. Okay, whenever there you require a communication between a processor and the input and output device, your IO device will first interrupt your processor. It will initiate an interrupt signal. Okay, it can be, this interrupt signal can be initiated from the peripherals. Okay, so your interrupt will be initiated. Okay, in the whenever there is an interrupt occurs, your processor will come and provide the service. That is nothing but it will read the data from the input device, or it needs to send the data to the output device. That can be done whenever there is an interrupt occurs. Okay, so in this interrupts, there are basically you are going to have two types of interrupts. One is non-vector interrupts, and the second one is just nothing but your vector interrupts. Non-vector interrupts are nothing but your fixed branch address. You are going to give the fixed branch address, whereas in the vector interrupts, interrupt source supplies the branch address. Okay, interrupt source will be going to supply the branch address. This is known as a vector interrupt. Okay, non-vector interrupt, you are going to have fixed branch address. In the vector interrupt, the interrupt source supplies the branch address. The interrupt source only will supply the branch address. So if you see here, just on how the IO device and CPU and the interface models are connected. Here if you are going to see, from the processor you are going to give the data to the interface. So it can be given from the data bus, address bus. Okay, and there are two different operations we need to perform. One is nothing but your IO read or IO write operation from the IO device. This interface unit will have its own data registers, and it is going to have its own status register and flag bit. And then you are going to have the IO device. So you are going to communicate with your IO device using the interface unit. So you will be going to have the IO bus, you are going to have the data valid, and you are going to have the data accepted. So valid data is there or not. Okay, the data which you have sent by the interface, yes, it is valid and I have understood the data. That information is given by the IO device. Next is something but your interface will be asking that have you accepted the data. Okay, so that is something but your acknowledgement signals. Those are, first it is read the status register, check the flag bit, whether flag bit is 0 or 1. If it is 1, it's going to go with a read the data or register. Okay, then transfer the data to the memory and complete operation completes, then returns back to the read the status register. Okay, if it is not, if the operation is complete, continue with the program. Software consideration, we need to do the software consideration. So there are IO routines, software routines for controlling the peripherals and for transfer of data between the processor and peripherals. IO routines for standard peripherals are provided by the manufacturer itself. Those are nothing but your device drivers, OS and BIOS. IO routines are usually included within the operating system. IO routines are usually available as operating system procedures. Okay, what do you mean by actually? You mean by IO routines? IO routines are nothing but your input output subroutine programs. When an interrupt is generated from the IO devices, your processor will stop executing its own work and it goes and provides the service to those IO routines. So to provide that service, we need to run certain program for that particular service. For providing that service, we are saying it is an IO routine program. So the software routine pros for controlling the peripherals and for transfer of data between the processor and the peripherals. So we do have a software routines which is used to control the peripherals and the transfer of data So between the peripherals and the processor, we will be using a software routines. These IO routines for standard peripherals are provided by the manufacturer. Generally, these IO routines, input and output device routines, are nothing but it is a device drivers. Okay, generally when we connect your device to your system, I cannot operate my device, so first I'll install the drivers into the system. Later on we will be going to start communicating with those particular device. So that communication to communicate with that one, that interface unit is nothing but it is nothing but your subroutine program. That you can say it is an IO routine program. So that IO routine program we are going to install in the system. So those we are saying it as a device driver or OS or BIOS. These IO routines are usually included within the operating system only. These IO routines are there within the operating system only. IO routines are usually available as operating system procedures. These IO routines are usually available as an operating system procedures. You are going to have a system procedures are there. Those are nothing but your operating system or BIOS function calls. Okay. Next is nothing but your priority interrupts. When we go with the priority interrupts identify the source of the interrupts when several sources will request service simultaneously. Determine which condition is to be serviced first when two or more requests arise simultaneously. Priority interrupts are nothing but when you go with an interrupt concept. So when we go with an interrupt concept is nothing but the IO device will interrupt your processor for going with the communication. But now, as if you are going to see, this interrupt can be done by at the same time by two or more devices can interrupt my processor. At that instant of time, the processor needs to decide that for which device it needs to provide the service. For that case, it uses a priority interrupts, that is something which a first come first service basis, or it can use some other polling or some other concepts also that you will be going to study in the coming subjects. But let us discuss in short what is priority interrupts. Priority interrupts is nothing but your first come based upon the priority of those one, it will provide the service. Okay, now when we go with this interrupts, we do have a software priority interrupt and the hardware priority interrupts. When you go with the software priority interrupts are nothing but your polling, and the hardware priority interrupts are nothing but your desi chain and parallel priority. What do you mean by polling? Identifies the highest priority sources by software means. So by using the software, your particular processor will identify that which particular device is having the highest priority. Based on that one, it will going to provide the service. So one common branch address is used for all the interrupts. Program polls the interrupt source in sequence. The highest priority source is tested first. Okay, so that is nothing but you'll be going to have only one subroutine program or IO routine program for the polling, where you will be going to give that or these particular devices have been asking for the service. So all the device addresses you will be going to provide as an input to this particular program, software program. So this particular software program will give you the information that which particular device is having the highest priority. It will test that highest priority, and it gives the information to the processor that you need to communicate with this particular highest priority device. Okay, for that will be everything will be done by using the software means only. Polling priority interrupts. If there are many interrupt sources, The time required to poll them can exceed the time available to service the IO device. There are many interrupts are there. So for all those interrupts, I need to check the that is something but yeah, which is having the highest priority, each and every interrupt. So for that, for polling that, all the interrupts may take more time when compared to providing the service to the IO device. Okay, that will act as a disadvantage of this pooling concept. Next one is what known as an hardwired priority interrupt. In the hardwired priority interrupt, we are going to have the daisy chaining and daisy chain and parallel priority. In the daisy chain, if you are going to see here, let us come with the daisy chain. Here I am having device 1, device 2, device 3. Okay, and for all these three devices are connected to the CPU. Next, all these three devices have been requested, interrupt request has been sent for them. Okay, now what we are going to do, how we are going to acknowledge those devices that this particular device will give the priority. Okay, so one stage of daisy chain priority interrupt arrangement. No interrupt request. We don't require any interrupt request. Invalid interrupt request but no acknowledgement. So then someone have interrupt the request but there is no acknowledgement. No interrupt request passed to other device. Other device requested interrupts. Interrupt request. Now if you see here, it's a small daisy chain diagram type. Okay, how it is going to handle that interrupt request. You're going to have intact priority interrupt in, okay, and you're going to have the interrupt request from the device that is given to the SR flip-flop. From there you'll be going to get the output. Okay, so this output will, based upon that particular output, it is given to the AND gate and it gives the information that yes, there is a priority output is there. Okay, next it is going to enable the vector address. It is going to enable the vector address. So based upon that vector address, it goes to that particular vector routine program and it will execute that particular program. So this will occur in the daisy chain. Coming to the parallel priority interrupt. In the parallel priority interrupt, you are going to have the priority encoders. Okay, when parallel priority interrupt enable flip-flop. Interrupt enable flip-flop will be going to set or clear by the program. Interrupt status flag, which is used to set or clear the encoder output. Okay, priority encoder table. Interrupt cycles. At the end of each instruction cycle, a CPU checks your interrupt enable and interrupt status flag bits. If both are is equal to 1, then CPU goes to an instruction cycle. Sequence of micro operations during the instruction cycle. It provides sequence of micro operations. This is an input interrupt register. You are going to have disk, printer, reader, keyboard. Okay, so each and every IO device will have its own interrupt register. Okay, based upon that interrupt register, this interrupt register value will be given to the priority encoder, which gives you that based upon which interrupt is having the highest priority. Thus, interrupt output will be given to the validate to the CPU. Okay, next one is nothing but your mask register is nothing but your If a particular register, if all these register interrupts, then the only one will be need to service and the rest all should be under the masking condition. I need to stop it. So though that is nothing but your mask register. Okay, next we are going to have interrupt enable and interrupt enable and interrupt status flag bits that will be going to interrupt the CPU and gives the information that this is a validate this is a particular interrupt IO device which needs a service from you, and this is your valid address for that one. So based upon that one, your CPU will going to function. Initial operations of IOSR. So clear the lower level of mask register bits, clear the state interrupt status bits IST, save the contents of the processor register, set the interrupt enable bit, and proceed with the inter service routines. And final operations will be your clear the interrupt enable bit and restore the contents of processor register, clear the bit of the interrupt register, okay, and belongs to the source that has been serviced. Set the lower level of priority bits in the mask register, restore the return address to the PCE, and set the interrupt enable. So those are the steps which is going to occur. Now if you see here, this is your memory. Your main program is been executed, okay, at a particular part, okay, and to suppose at 749 and memory address, your keyboard have been interrupted. Okay, so what happens, it goes to the program service routine of your keyboard. It will execute that particular program and return back to your main programs. So whenever the CPU jumps from your main memory to the subroutine program to provide the service for your IO services, then it needs to store the memory address of what present memory location. What is my present memory location? It is 749. What is my next memory location? It will be 750. That 750 will be moved into the stack memory. I am moving the 750 memory location into the stack memory. Okay, then it reads the data called 256 of your IO subroutine service program. Okay, this IO routine service subprogram memory address will be read, and it goes to the IO service program where memory address 256, and it executes the program. It will execute based upon my keyboard service. Okay, that keyboard service program will be executed, and after doing that execution of this IO service program, it will be going back to the main memory. To go back to the main memory, first it goes to the stack memory. It retrieves the memory address 750 memory location. Based upon that 750 memory location, it goes to the 750 memory location main memory, and then it will be going to execute. It will restart its execution of your main program. So that happens in the interrupts. Okay, interrupt initiated IO devices. In the next class, we will see about the DMA. What actually you mean by DMA? What is processes? All these things we will be getting into the will get in next class. Thank you.